Recording, all of you are receiving the recording? Hello?
Yeah, recording
yes, sir.
is on.
Yeah, because I have not received the recording.
Oh, no, you will not receive it. Actually, the link is there on the WeLearn portal. If you click it, then everyone can see it.
Okay,
I can
fine,
send you the link.
Yeah,
I can,
yeah.
Ma'am,
It is actually the old link.
Yeah.
If you have the old one.
Yeah, what are you telling? Somebody wanted to ask you something. Yeah.
oh, I am telling that thing that the link is provided in that folder. We have I have seen that the lectures video of second years probably. Also, I am confusing there.
Oh.
No, both. Actually, I cannot make another folder. You can only add one folder.
Okay.
So the second year videos are also there, and the fourth your video is also there.
Okay. I'm sharing the screen, so can you put yourself on mute so that background noise is less. Okay, please let me know if you can see the screen. Are you able to see the screen? Hello?
Yes, sir.
Yes, sir.
Okay, fine. And just for my knowledge, it is 4211, right? The course number is 4211, right? Yeah.
Yes, sir.
Yeah. Okay, so I think we have been discussing the basic quantum mechanics, and in which we eventually highlighted that our job will be to calculate the stationary states of Hamiltonian. So this is going to be the major challenge, stationary states of Hamiltonian. And if an operator, so that means essentially we will be solving the equation for H psi equal to E psi with a focus on the ground state solution, because as of all of you know that there are several solutions. So we write it EI psi I, and a more conventional, I mean, this is of course depends on you, a more conventional way to write the quantum numbers for the Hamiltonian is from 0, 1, 2, etc., such that E0 is less than equal to E1, less than equal to E2, and so on. So this factors the possible degeneracy among the states. So I have written equal to. So E0 becomes my ground state. Okay. And corresponding wave function becomes psi 0. So at the beginning, I should say that our focus will be more on this, though on certain contexts we'll also discuss what happens to the other states, excited states. And particularly, we will discuss a method when you go electron correlation, which is called the configuration interaction, in which the excited states come very naturally. So we will discuss that, but the focus will remain on the ground state. But I just want to tell that this is the solution which will be the focus of our quantum chemistry course. For all other operators, A, which commute with Hamiltonian, okay, the psi 0 or psi I, whatever, is also an eigenfunction of the operator A. And this is something that we have learned from basic quantum mechanics, that if two operators commute, they have simultaneous eigenfunctions. So in which case, it's very easy to measure the value of the operator A. That's the corresponding eigenvalue. If the operator A does not commute, so this is, I'm now talking of other operators. So obviously I have solved this eigenvalue equation of the Hamiltonian, but that gives me only energy. We want to calculate many other properties. So that is why I'm talking of other operators. So if it commutes, then it is very simple. If A does not commute, then of course we resort to the average value description, which is for the ground state psi 0, A psi 0, and divided by psi 0, psi 0. So that's a more general situation. Of course, if psi 0 is normalized, you don't have to write the denominator. Correct? So this becomes an average value expression when it does not commute. Either way, you can see that this average value expression is good for both case 1 and 2, because if it does commute, anyway the average value will give you the eigenvalue. Okay? So we don't have to bother. And if it does not commute, then it becomes a non-stationary state of A. Then as per the quantum mechanics, you know that if you make a measurement in the Copenhagen interpretation, you don't get a specific value, you get the eigenvalues of the operator A with some probability. And then the only description that you can give is an average value description, and we have justified this. I think those who remember my second year course, I must have justified this from the probability that if I expand the psi 0 in terms of the eigenfunctions of the operator A, then how much each eigenvalue is contained will depend on the overlap between that eigenfunction and the psi 0, and mod square of that will be the probability. Take an arithmetic average, it gives you the average value. I think this is something that I have derived in many classes in the second year when I do this. So what I'm trying to say that for our purpose, we will try to solve this. And after whatever solution we do, we will try to look at the average value for other operators. Of course, if I have solved this, the average value of the Hamiltonian would also be the energy in any case. So I think that's really beside the point. So this procedure is something that we can do for one electron problem. Okay, also. So for example, harmonic oscillator. If you remember the simple harmonic oscillator, SHO, we had calculated the wave function. Then we asked you, what is the average value of X, if you remember? What is the average value of momentum? What is the average value of X square? What is the average value of Px square? And so on. So there are so many questions you can ask, right? So we ask this question as an average value because that is not an eigenfunction of momentum, for example. Okay, so that's the reason, or position, for example. So that's the reason we have to talk about the average value. And that's true for the hydrogen atom as well, where you talk of the R average and so on, where the average value of the position of the electron in a hydrogen atom, let's say 1s orbital. So we have done this for one particle problem. I'm just repeating the status of the quantum chemistry, what we are actually planning to do, either one particle or two particle. On the other hand, if they commute, then the average value is same as the eigenvalue of that operator A. And those are called then the symmetry operators because they commute to the Hamiltonian. And those together form the groups, all the symmetry operators together form the group in a molecule. And that is on any system. And that is something that we have done in the group theory course. That by defining these operators which commute to the Hamiltonian, we can then predict the wave functions much more simply, the symmetry properties of the wave function. And then there are lots of advantages that you already know. For those who have done the group theory course in last semester have already gone through this. Okay, so that's the entire scenario. What we are now planning to do is to extend, and this is the main purpose, extend the one particle to many particle problems. So that is the first part that we have to do. Because our single particle problems like particle in a box and all that are really model problems. So for example, if I go to atoms and molecules, there are many electron problems, right? So the first thing that I would like to say, what are the properties in terms of symmetry that these one or many particle problems have? Okay, in particular, of course, many particle problems. Before I do that, I must at this point also introduce, which has been already done again in the second year, probably at some point of time in the physics course at least, the spin. That the electron has two spins. There are two spins. One of them is called the up spin or alpha spin. Another is called the down spin, that is beta spin. So to be more precise in a coordinate representation, and this I should now write very clearly, the wave function will not just be a function of x, y, z or r theta phi, but a spin coordinate which I'm calling omega. So in general, I can have psi x, y, z omega. Okay? And if I add this omega, there are two kinds of omega, that is alpha omega or beta omega, by this name that one of them corresponds to upspin, one of them corresponds to downspin. If you also remember, any single one particle wave function are called orbitals. I think you remember our definition of an orbital. An orbital is simply a one electron function. When I add the spin, it becomes a four coordinate function, not four-dimensional function. And these kind of functions will be called spin orbitals. Just the notations, I'm trying to first clear it out. So there will be a definition, there will be a difference between orbitals and spin orbitals. Orbitals will only depend on x, y, z, a three-dimensional space function. And the spin orbitals will depend in addition to a spin coordinate. And as a function of spin coordinate, there are only two functions, alpha and beta. To distinguish the orbitals and spin orbitals, what we will now use for the spin orbitals, a new notation, and that I will try to, that is as far of the notation used by Szabo and Oslund. Again, for the person who did not attend, I think Roy, we had given the reference of Szabo and Oslund as the main textbook. So for the spin orbitals, usually in Szabo and Oslund, the notation that is used is chi. And for orbital, we can use phi or whatever. Let's say for orbitals, I use phi. Just to identify orbitals, I use phi. Then I can show that given a set of phi, let's say a set of phi is there, phi I, and a set chi j is there, then a chi j can be built by multiplying phi with either alpha omega or beta omega. So phi is a space coordinate, omega is the spin coordinate. You multiply by alpha and beta to the spatial orbitals, you get the spin orbitals. So the number, so given a set of spatial orbitals, let's say k number of spatial orbitals, remember, these are nothing to do with eigenfunctions. I'm just talking of any one electron function. Given a set of k spatial orbitals, we have 2k number of spin orbitals. I hope it's clear for all of you. Because each of them can be independently multiplied by alpha omega or beta omega, alpha or beta spin. So that is very important to remember, that when we frame the wave function for many particle problems, we will frame it in terms of spin orbitals, because the one particle problem, remember, the spin was not important because it has only one electron. Whether it is this or this, it does not matter. But as soon as I put two electrons, it is important to note what is the relative spin of one electron with respect to the other. I hope you understand. So the spin must come in explicitly. For the hydrogen atom, the spin was also there, but we did not bother. So for example, for hydrogen atom, we said you have a 1s orbital, r theta phi, but that could be multiplied by alpha omega or beta omega. It is immaterial. The energy is same. It does not bring in any new physics. So that is the reason we did not bother. But in principle, even for hydrogen atom, spin orbital existed. But when I come to, let's say, even two electron problem, it is explicitly important to talk in terms of spin orbital. So that is something that I first want to say, because there is a relative orientation of one with respect to the other, and they are not independent because they are now coupled problem. It's a two electron problem, right? Of course, if they are decoupled and becomes a 2-1 electron problem, then it's a completely different thing. So we will come and discuss that later. But in general, we have to describe it in terms of spin orbitals. So given a set of spatial orbitals, we can say how to construct the spin orbital by simply multiplying alpha omega and beta omega. So the space orbitals have 3 coordinates, spin orbitals have 4 coordinates. With that, as done, we will now try to extend the one particle problem to the many particle problem. Remembering that whatever coordinate system that we will use or we will talk, they are actually spin orbital coordinate system. That includes spin. So that's something that you have to remember in your head. Okay? So now let me come to a very simple problem first of a two electron problem to describe the symmetry. Now, what I'm going to first discuss is a two electron problem, but a more general problem would be two quantum particles, not necessarily electrons. We know there can be other quantum particles like bosons and so on. So what we'll discuss is a quantum particle first. So what distinguishes a quantum particle from the classical particle? All of you must have done statistical mechanics, that you know that the classical cricket ball, if I have 10 balls, I can identify them. So in classical mechanics, the particles are distinguishable. Whereas the fundamental principle of quantum mechanics is that the particles are indistinguishable. If I have more than one particle, I cannot say which is electron 1, which is electron 2. Though I will have set up coordinates, that's completely different. But I can't say this is electron 1, that is electron 2. So one of the fundamental points of the quantum mechanics is that the particles are indistinguishable. So if you remember, there are two kinds of statistics, two types of statistics, one for distinguishable particles, one for indistinguishable particles. And we will see that even for this, there are two subsets. So eventually it becomes three statistics that you did. The classical statistics, I must remind you, is what is called the classical Maxwell-Boltzmann statistics. So Maxwell-Boltzmann statistics you must have read in statistical mechanics in both physics and chemistry. So that is classical. What we are discussing is a quantum particle, and we want to look at how the system, what kind of symmetry the system had. So let me first write down the Hamiltonian for two particles. So H of 1, 2. By the very fact that they're indistinguishable, I can write this as H of 2, 1 without any loss of generality. So that's a very important symmetry of the Hamiltonian, that the two particles are interchangeable. So whichever way you write, kinetic energy of electron 1, kinetic energy of electron 2, potential energy, everything is interchangeable. So without even writing the Hamiltonian, I can argue that since they're indistinguishable for quantum particles, I'm now talking of specifically quantum particles, the Hamiltonian remains invariant with respect to the interchange of the two particles, coordinates of the particles. I'm again talking very generally now of quantum particles and not necessarily electrons. Such a Hamiltonian, I would argue, is a Hamiltonian which commutes with what I now define an operator which is called the permutation operator. Let me first define a permutation operator. Let's call it P. So a permutation operator, a two-particle permutation operator, general property is that if it acts on a function psi, whatever is the function psi, it's a mathematical definition. So this is nothing to do with indistinguishable, distinguishable. It just gives you the same wave function with one interchange to two, two interchange to one. So I hope it's very clear. Why am I calling it a permutation operator? So it simply permutes the coordinates of the function. It doesn't do anything more. So that's the definition of the permutation operator. I think most of you may have attended my class in second year where I defined a Hamiltonian which is parity invariant. I hope you remember for the harmonic oscillator. Eigenfunctions, it is actually symmetric, plus x, my even function, right? And I argued from there that it's a parity invariant, so the eigenfunctions must be odd or even. There is a proof. This proof that I'm going to do is very similar to that proof. Very similar, as you will see. All of you which remember would actually see this. So I'm first saying that that's the definition of the permutation operator. Then I'm saying that this Hamiltonian commutes to the permutation operator. So I'm going to prove that first, which means HP is equal to PH. That's what I'm going to prove. So I have to prove that HP is equal to PH. So how do I prove? I take any arbitrary function psi. So this is for an arbitrary function psi. Remember, again, I am restricting my discussion to two particle problems. But again, it's a general problem. Permutation is a pair permutation. And any three particle permutation, I will not go into it, can be written as a product of two particle permutation. So I'm not going to worry about it right now. But I'm just saying that if HP acts on a psi, what will happen? Any arbitrary psi. So first P will act on psi. So I will have H, which is now H of 1, 2. That's how I start. P psi of 1, 2 will give me psi of 2, 1. So initially, this was all 1, 2. Right? So I get H of 1, 2, psi 2, 1, very simply because P is simply permutes. It doesn't do anything else. Then I take up PH psi. So the right hand side. Again, 1, 2, 1, 2, everything is there. Now P does not act on psi. P acts on H psi. It's important to realize on the right of it, just like the parity operator. Then it will now permute in parity operator. What is happening? Plus X was changed to minus X, if you remember. Here, I'm interchanging 1, 2 to 2, 1. So H12 psi 1, 2 will then become H21 psi 2, 1. I hope it's clear. It will interchange the coordinate here as well as here. Sorry. H21 and psi 21. However, for the quantum indistinguishable particle, I know that H21 is nothing but H12. So I can write this as H of 1, 2, psi of 2, 1. You can now compare these two. So I can say that HP psi equal to PH psi for any arbitrary two particle function. Again, I'm just taking two particle, but please, it can be easily generalized. And hence, I can now argue that H commutes to the permutation operator. I hope it's clear. And again, those who remember that parity operator proof, it's very, very similar. Is that okay? Anybody has question here? Hello?
No, sir.
Is okay? All right.
Yes, sir.
Good. So now, if you remember, the reason we look for symmetry, permutation, a commutation operator, is that instead of looking for the solution of the Hamiltonian, which is very complicated, we want to first investigate what are the solutions of the permutation operator, because they have common eigenfunction, right? So now I write P 1, 2, and now I write the eigenfunction specifically phi, just to distinguish from psi, which is an arbitrary function. So this phi 1, 2 now is an eigenfunction. So I have a lambda times phi 1, 2. So let me look at what is the nature of phi 1, 2. I am now searching for eigenfunction of the permutation operator. Okay, so to do that, again, I use the same thing that I did for the parity operator. I apply the permutation operator twice on the eigenvalue equation. So first time it becomes lambda phi 1, 2. Then parity operator will act again on phi 1, 2, and so on. So then what will happen the first time, it will make this phi 2, 1. Oh, sorry. It's an eigenvalue equation. So I will have phi 1, 2. Again, P 1, 2, phi 1, 2 will become lambda phi 1, 2. So I will actually get lambda square phi 1, 2. So this is by application of eigenvalue equation twice. However, I can write this by definition without knowing this. For any phi 1, 2, including eigenfunction, this changes to phi 2, 1, again changes it back to phi 1, 2. So this should be equal to phi 1, 2, right? So this is by definition. This is by application of eigenvalue equation. This is by definition. And both must be equal. So lambda square phi 1, 2 must be equal to phi 1, 2. So lambda square equal to 1, lambda equal to plus minus 1. right? It's very simple theorem. Again, if you remember, those who remember the parity operator theorem, it's exactly identical. Now that I know lambda, I go back to the eigenvalue equation. So I write P12, phi 12 equal to plus minus phi 12, right? Because it's a lambda times phi 12. Now on the left hand side, apply definition again to the LHS. So that I will get phi 21 equal to plus minus phi 12. So I reached my result that I wanted. So you can see the proof. I started from here. I applied P12 twice, and by eigenvalue equation, just by eigenvalue equation, without using the definition of permutation operator, I will anyway get this. The same thing if I do with the definition of the permutation operator, I will get just phi 12, which means lambda square must be 1, lambda must be plus minus 1. I go back here and then apply the definition to the left hand side. I get phi 21 equal to plus minus phi 1. Is it all? Everybody understood this up to this point? This is exactly how we said for parity operator, it will be plus x equal to plus minus minus x, odd or even. In this case, we can see that the wave function will be either symmetric or antisymmetric. This is called antisymmetry, minus, with respect to the permutation of two particles. Permutation of the two particles are the coordinates of the two particles. It doesn't matter. So what we are actually looking at is the coordinates definition. And now, without any further ado, there are proofs. Actually, there are experiments which have actually shown this. But without going into that, let me say the ones which follow the symmetric wave statistics are actually called the bosons. And the antisymmetric ones are called the fermions. I think this is something that you already have done. You already have done it in several times. But I just thought I will mention this. So these particles follow what are called Bose-Einstein statistics. This particle follow Fermi-Dirac statistics. Of course, Bose, you know, S.N. Bose here. So it's the same person who actually did this. So that's one of the very good Indian contribution that I can immediately cite. So without further ado, I would say that the electrons, and that is something that came from the experiments, electrons actually obey Fermi statistics or Fermi-Dirac statistics, and thus are called the fermions. Which means for electrons, it will be a negative sign. So that you remember that anytime I write a wave function for the electron, any wave function, psi, phi, whatever, they must follow this rule. For the electrons. And for the Bose particle, there will be plus. So that's very important. But this plus and minus will change everything. In fact, because of the symmetrization in the Bose particle, you can put many, many particles in one orbital. You will see that later. And that led to the Bose-Einstein condensation, which is not there for the electrons. Electron, there will be lots of constraints. So in fact, this minus and plus are not trivial. That will change a lot of things. But as of now, let us first say that the Hamiltonian eigenfunctions of the Hamiltonian, they are also eigenfunctions of the permutation operator because of commutation. And with that, we can say that the quantum eigenfunctions will be either symmetric or antisymmetric. We are, in our class, we are only dealing with electrons, because we are also under Born-Oppenheimer approximation. We are not talking of the nucleus at all. So we are actually depending on the electrons. We are looking at the electrons. So the electrons will obey the anti-symmetric statistics and the fermions. How to do this, that we'll see later. So I think at this point, this should be first made very clear. So whichever way we form the wave function, eventually there should be antisymmetry. Okay? Without this symmetry or antisymmetry, knowing whether the wave function is either Bose or fermion, let me first state another very important theorem. And that is, again, has been stated in many times whenever I teach, I do state. That is the non-interacting theorem. So this theorem is very simple. Let's assume that I have two particles. Again, two particles are simple, so that's why I'm discussing everything in two particles, which are not interacting. So that's the meaning of non-interacting. So I simplify my problem and see what happens. So let us say that I have a H of 1, 2, which is a sum of H of 1 plus H of 2. I hope all of you agree that such an Hamiltonian would represent the two non-interacting particles. Just 1 minute. Yeah. So where H of 1, small h of 1 and small h of 2 are nothing but the the one electron Hamiltonian for two particles. Again, for each of these particles. Again, I'm not discussing how to get these. They are, of course, indistinguishable, as you can see, because h of 1, 2 will be equal to h of 2, 1, because it is simply plus. So, and everything will be following. So this is a non-interacting theorem where my Hamiltonian is h of 1 plus h of 2. This essentially means that the electrons 1 and 2 do not interact with each other. What I'm trying to tell that in that case, the many particle problem is very simple. Whether it is Bose, fermion, doesn't matter. So how it is simple? The wave function or the eigenfunction for this Hamiltonian can be constructed from the eigenfunctions of the one particle problem. And one particle problems we are already expert in solving. And that is what we have done in the previous classes. So let's assume that I know the one particle problem. So let's say h of phi I, and let's say my coordinates are r omega. Again, I will describe in terms of spin orbital simply because I'm eventually going for two particle problem, right? As epsilon I, phi I, r omega. So when I'm writing r as a vector, it means it is x, y, z, r, theta, phi, whatever you want to create. So I know the solutions of the Hamiltonian. Whatever is this h, it's a one particle problem. It can be a problem like harmonic oscillator. It can be 3D harmonic oscillator. It can be hydrogen atom, whatever, doesn't matter. So then I would say that this Hamiltonian eigenfunction can be constructed in terms of a product of these Hamiltonian, these orbitals or spin orbitals. So let me take a product of phi I r omega, so r1 omega 1, and a phi j r2 omega 2. Now, of course, we already know that if I take such a product, I have to worry if it is electrons, is it antisymmetric or not? I'm going to come back to that. But let's take a simple product and allow h of 1, 2 to act on this. I have taken one of the functions as phi I, one of the functions is phi j, doesn't matter. Whether I is equal to j, I is not equal to j, we'll see later. So this now can be written as h of 1 plus h of 2 phi I r1 of omega 1 phi 2 or phi j, sorry, r2 of omega 2. And now I will allow h1 to act. h1 obviously will act only on this because this has the coordinates of 1. It cannot act on r2 omega 2. For h of 1, this will actually be a constant. So then this would then become ei phi I R1 omega 1, because I'm now using, this is an eigenfunction of H of 1, H. So it is a general thing, 1, 2 I have not written. So EI phi I R1 omega 1, and this will become now a constant, phi j R2 omega 2. I hope all of you can see the point. The next will be H2. By the same logic, H2 will not act on this, but H2 will act on phi j. And H2 acting on phi j will give you Ej. So this will now become plus Ej. Phi I will become a constant. So I will write that first now. And phi j R2 omega 2. So H2 acting on this will give you Ej phi j R2 omega 2, such that I can take this as a common and write this as EI plus Ej phi I R1 omega 1 phi j R2 omega 2. So this Hamiltonian acting on this gives you the same function with this as the eigenvalue. So you can see that a product of these eigenfunctions, one electron eigenfunction, is an eigenfunction for the non-interacting Hamiltonian with the eigenvalues which are summed. So this actually tells you a very simple way to remember that the wave function is what is called multiplicably separable. I mean, it's in English, but you'll be able to understand this. And the energy is additively separable. So this is one, the whole idea of separable is coming because it's a non-interacting problem. So I'm able to separate the eigenfunction, which means I'm able to write the eigenfunction as a product. That's the meaning of multiplicably separable. Whereas the eigenvalue for the whole of H of 1, 2, I can write as a sum of EI plus Ej, corresponding EI and Ej. So this is a very simple way to remember the result of the non-interacting theorem. The wave function is a multiplicably separable, energy is additively separable. So this is a very general theorem. Now, of course, for bosons and fermions, I know that I have one more level of examination that I have to do. Is this function symmetric or antisymmetric? That would be a very important examination. Otherwise, I cannot allow this function to be an eigenfunction of this Hamiltonian, quantum Hamiltonian. So it of course depends on whether I is equal to j, I is not equal to j, so many things. So let's assume I is equal to j. So the indices of the spin orbitals are identical. Then my wave function becomes, I will write it down, phi I R1 omega 1, phi I R2 omega 2. Right? Because I is equal to j. Such a wave function very clearly is a symmetric wave function. Now we have a symmetric wave function. In terms of spin orbitals. Clearly, if I is equal to j, it can be a boson, but cannot be a fermion, unless I do something. In the way that is written. We will see if there is any way that we can antisymmetrize this. But let us see at this point of time, if there are two spin orbitals, I can put two electrons, two bosons, but not two electrons. And I think you are already getting to that Pauli exclusion principle, right? Pauli exclusion principle already states this, and you will see that that is going to happen because it's no longer antisymmetric. So first of all, a simple function like phi I will not be acceptable because it's not antisymmetric. You will try to antisymmetrize, then we will see what will happen. All right. Before I do that, let me take the case of I not equal to j. If I is not equal to j, you have a problem because this function as it exists is neither symmetric nor antisymmetric. I hope it's clear. Because this is I, this is j, and they are two different functions. So even if I interchange, I will get a different functions. Of course, remember when I said the wave function must be symmetric and antisymmetric, in mathematics, there are functions which are neither symmetric nor antisymmetric. In fact, most functions are of that kind. Many particle functions. So this is, of course, as it exists, it is neither symmetric nor antisymmetric. However, since each of the product is an eigenfunction, I can take the product in a different order. That is, this can be j, this can be I, and mix it. I'll still get the same energy. So for example, if I take a product phi I R1 omega 1 into phi j R2 omega 2 plus phi I R2 omega 2 into phi j R1 omega 1. So I hope you understand what I'm doing. I'm interchanging 1 and 2. Sorry. I'm interchanging 1 and 2 coordinates. If you look at the whole wave function, each of these is a product. So each of these has an eigenvalue ei plus ej. And of course, the full wave function will also have an eigenvalue ei plus ej. If it is not normalized, I can always normalize. In fact, it's the easy way to normalize is by multiplying by 1 by square root 2. I can tell you that. That's not important. But this function, if you look at this composite function, this is now symmetric. I hope you can see this. Why? Because if I interchange 1 and 2, the first part will generate the second term. And the second term will generate the first term. But because it's a plus sign, it doesn't matter. So if I is not equal to j, this will be a valid function for bosons. As I said, if I is not equal to j, as such, this cannot be either a boson or a fermion. Because this is neither symmetric nor antisymmetric. Is it clear? If anybody has question, you please ask me. This is a very important point that I'm talking here. Okay? If I is equal to j, it is symmetric. If I is not equal to j, it is neither symmetric nor antisymmetric. So then I can say I interchange the product 1 and 2, then do a plus sign, then it becomes symmetric, and there's a boson. If I understand that, I could now do exactly the opposite. The interchange is phi I R1 omega 1, phi j R2 omega 2 minus phi 1 R2 omega 2, phi j R1 omega 1. So now take the negative side. And now you can see this is antisymmetry. Which is for fermions. Right? The first term becomes the second term becomes the first term, but they have a negative sign, so it will become a minus of that. So it's an antisymmetric, and now this is a valid function when I not equal to j. I can actually construct the wave function for this product. So given a product, phi I, phi j, R1 omega 1, phi j R2 omega 2, I can always construct an antisymmetric product by taking a minus sign and interchanging for two particles. It is very easy to show that you can actually do this similar exercise for 3 particle, 4 particle, and so on, 3 electron, 4 electron, and so on, either for boson or for fermion. We will not worry about boson for this course, we will worry about fermion. So the fermions would be done by similar procedures starting from this, and let me call this some antisymmetrizer. So A is an antisymmetrizer. I will not worry about it right now. How to antisymmetrize, we'll see later. I have given you one example, how to antisymmetrize by minus sign. But obviously when electron number will be 3, 4, 5, it will be complicated. We will see how to do that. There will be so many permutations that are possible. But let me say I have antisymmetrizer. So I will write only one product. Write this. You will know that this function is antisymmetric. Is it clear to all of you? It's just a symbol instead of writing every time this. Now you can wonder, when I was equal to J, it was fermion. It was a boson, sorry. I could not construct fermion. You may think, can I do similar to this with a minus sign? You can try, but then what will happen? Both are I. So as soon as you interchange, both are same. So this will actually give you 0. This is I, this is I, this is I, this is I. So any antisymmetric function that you try to construct will actually vanish. So whenever I is equal to J, it is not possible to construct an antisymmetric function. Just 1 minute. Just 1 minute. There's a phone call. Hello. हाँ बोलो. হ্যাঁ এখন প্রবলেমটা হচ্ছে যে I have not been able to tell him that we have some limitations right now, the number of posts. I will talk to you. So হ্যাঁ রেস্ট্রিক্ট করে দিয়েছে না আমি ইন্ডিকেশন দিয়েছি যে আমাদের অলরেডি রিজার্ভ পোস্টগুলো এখন ফিল হবে তারপরে যে কটা পোস্ট থাকবে দেন উইল সি এখন আমাদের রিজার্ভ পোস্টগুলো আগে ফিল করতে এখন তো রিজার্ভেশন এসে গেছে so I told him that it may take time but I did not say there are no positions after reservation করার পর আমার হাতে 3-4টা পজিশন থাকবে হ্যাঁ নমিনেট আপনি করতে পারেন বাট আই এম জাস্ট টেলিং ইউ দ্যাট দিস উইল রিয়েলি রিকোয়ার টাইম বিকজ হ্যাঁ ওটা একটু আপনি ভালো করে বোঝান যে একটু পরে করা বেটার right that will be good okay thank you হ্যাঁ ভালো অনেক দেখা হয়নি হ্যাঁ ভালো আছি okay thank you okay you are doing okay right all good okay thank you bye I'm sorry, I went up the line. I'm sharing the screen again. Okay. Are you able to see the screen?
Yes, sir.
Yeah. So you can now see that if I is equal to J, what I was telling you, any method you try to do, you cannot antisymmetrize. It is not possible to construct. The wave function will actually become 0. And this is the statement of the Pauli exclusion principle in many ways. Because Pauli principle says that means any two particles cannot have the same functions phi I and phi j. That is what it means. Because I'm now constructing I equal to J, and these two functions, I and j, cannot be same. Right? So that is the context of the Pauli exclusion principle. Remember, of course, I'm always talking about spin orbitals. And Pauli exclusion principles say that the two electrons cannot have the same spin orbitals. If you remember, so actually it can be proved. But for the bosons, it is possible. But if I is not equal to j, even as it stands for boson, it is not symmetric. But for I equal to j, I can do both symmetric and both antisymmetric. I not equal to j. Sorry, I not equal to j, I can have both symmetric and antisymmetric. The antisymmetric ones we will keep discussing, and I have written an antisymmetrizer on a product, and that would essentially mean that I have antisymmetrized. So that's something that I'm going to use later part till I define what is an antisymmetrizer. I will define very soon, of course. Okay, so I hope this is a very good context to remember what the symmetry essentially means, and directly from the symmetry, the Pauli principle follows. So remember, Pauli exclusion principle is a very fundamental principle. It is as fundamental as the fact that the electrons obey Fermi-Dirac statistics. Because directly from the properties of the fermions, the Pauli principle follows. Okay. So that is a very, very important part to remember. To make matters somewhat simpler, I am going to now define a new set of coordinates, x, which should be a composite coordinates of r and omega. Because many times I have to write these two things. The reason I am defining x is that for orbital, we are hardly going to use Cartesian coordinates. We are always going to use r as a vector, which means r theta phi. For atoms and molecules, the orbitals have always r theta phi spherical polar coordinates. So they will not be using x, y, z anymore. So I'm using x as a 4-dimensional index of r and omega. I hope it's clear that I may use x. You can use x with bar or doesn't matter. I mean, as long as you understand, if you want, I can put this as a bar. So to indicate that this is now a 4-dimensional new coordinates for the spin orbital. So I would say, if I say phi I of x1, phi j of x2, that will actually tell you what I did before, r1 omega 1, r2 omega 2. So the antisymmetrized function that I wrote for electrons, I will simply write as phi I of x2, phi j of x1. So it's very simple to write. Okay? So that becomes my antisymmetric function, I and j, x1, x2 interchange. It doesn't matter, or I and j interchange, however, whichever way you want to see. So this is again, just to simplify. There's nothing new I'm doing, of course, but I thought I will right away identify the simplification. So I hope it is clear that if you have, first of all, the two things that we did, if we have a many particle function, they have to be symmetric or antisymmetric. So that's the first thing that I did today, because it's an indistinguishable particle. So the Hamiltonian is invariant with respect to interchange, and hence they commute to the permutation operator. So that is the first thing that I proved, how they commute to the permutation operator. And then I proved that the eigenfunction of the permutation operators are either symmetric or antisymmetric with respect to the interchange. So that is what I proved here by saying that the eigenvalues are plus minus 1. So this is this. So this is the eigenvalue of the permutation operator, not the Hamiltonian, of course. Please remember, the Hamiltonian eigenfunction is energy. Only thing that tells me that if two operators commute, they share simultaneous eigenfunctions, not eigenvalue. So none of these is going to help me in getting energy. Please understand that. But it's only the symmetry property of the wave function, that they must be either symmetric or antisymmetric. And that is a very important part of the quantum particles. Then, without proof, we said that the ones that follow antisymmetry are the electrons, which are called fermions. The ones that are called symmetric are called the bosons. Okay. Then we went to a very important theorem called non-interacting theorem, which can be applied to both bosons and fermions. And we said that if the Hamiltonian is sum of the two particle Hamiltonian, then of course, if I know the functions for eigenfunctions or spin orbital eigenfunctions for both h of 1 and h of 2. I can construct the total Hamiltonian as a product and the energy as a sum. But then I immediately notice the product itself is not allowed. It has to be symmetric product or antisymmetric product. We said that for I equal to j, only symmetric product is possible. For I not equal to j, both are possible. From the very fact of the I equal to j, that the fermion is not possible, it actually gives me the Pauli exclusion principle. Then I introduced the new definitions of X and a definition of the antisymmetrizer for the electron.
Sir,
Okay, is that okay? Yeah.
we have class from 10.
Yes,
so
I'm closing. So that nothing else I'm going to do. I just quickly revise. So this will be again sent, and tomorrow the class is at again 10 o'clock, right? 10 to 12.
Regarding the scheduling of
Yes, sir.
Yeah. Tell me 1%.
sir, we have talked to each other and decided timeline for the class. So this timing is okay with us. This Thursday 9 to 10, and we have blank. We have a free time in Monday morning 9 to 10, and after that 10 to 11 there is a class of advanced quantum chemistry already. So we if we can shift the Friday 10 to 12 class to Monday 9 to 11, and Friday 3 to 4 is already free for all fourth years. So Monday 9 to 11, Thursday
Monday 9 to 11, Thursday
9 to 10,
9 to 10, okay.
and
then
Friday 3 to 4.
3 to 4.
Yes, sir.
Why morning you want to be off?
No, sir. Means these are the timings that are free for all. Rest all are.
No. But what is the problem with Friday 10 to 12?
Oh, sir, that I told you earlier that Subhrangshu has a course on that time. So Oyan sir rearranged the timing in other two slots, but he could not manage that time.
Oh, okay.
Yes, sir.
So,
There's optics and atomic physics class at that time.
so it is a 2-hour class?
Yeah, he told to keep the 10 to 12 hour slot. Yeah, that's it. He told us.
So, yeah, I mean, I don't like the 3 to 4 slot actually, because Friday I keep some meetings here and there. So even the next Friday, okay, I will probably manage. Only 1 week I will have a problem, I think. Next Friday I will have a problem. After that, I think Sangita will be taking anyway. So
And
that should not be a problem, huh?
sir, are you planning to take the 4-hour class every week, or?
Yeah. I mean,
Okay,
1 hour will be tutorial kind of thing. I mean, we'll see.
Yes.
Every week is not possible. So maybe next week I can only restrict to this and skip the Friday class. Or Sangita can start this. Sangita, is it okay with you?
You mean from next Monday?
Next Friday, I have a problem.
From next Friday? Yeah, sure.
Next Friday, not tomorrow. Next Friday, I have a problem. So you are supposed to start after 2 weeks anyway, right? So,
yeah, I can start on Friday, no problem.
So basically just one class before, and then I will come in again at an appropriate time as we discussed.
Okay.
So we will see where
Friday, 3 to 4
3 to 4 p.m. Yeah. So otherwise, so tomorrow what will happen? Tomorrow is also 3 to 4.
It will go to from 3 to 4.
Tomorrow is it 3 to 4? Because tomorrow, if it is 3 to 4, I'm missing one class this week. I hope you understand.
Yes.
So I'm now concerned about tomorrow. Is that right, Sangita? That we'll be missing one this week.
Yeah, that's true. So we'll have only 3 hours this week.
Yeah, so tomorrow we're supposed to have 2-hour class. So how do I resolve it? From next week, it's okay. Because this Monday, I missed 9 to 11, no? So, and then eventually 1 hour will be missed here. 1 hour again, I have to give. So basically, I was thinking of 8-hour class. That will actually become 6 hours. If I miss 1 hour tomorrow.
Can we find a time tomorrow in the evening if it is okay for you?
I have no problem. Yeah, if you can go 3 to 5. Is it possible 3 to 5?
3 to 5, sir, I think not possible, because 4 to 5 there is class.
Sir, we have classes. This is best.
2 to 4?
Oh, sir, only free
Sir, only-
studies.
Yeah, 3 to 4 is.
Then but 1 hour. See,
Sir, you can do 5 to 6.
this week I'll be missing 1 hour then. No?
Sir, you can again continue from 5 to 6.
Okay, no problem. Okay, Sangita, please note it. Huh?
Yeah, okay. So 3 to 4 tomorrow and then again 5 to 6 tomorrow.
Okay, fine. And then but from
Okay.
next week, this timetable.
Yes, sir.
Sir, 5 to 6, I have some problem. Can you please shift it from 6 to 7? I think that
I
is
can shift it. You tell me one time.
3 to 4 and 6 to 7.
Okay. Is it all right for everybody?
Yes, sir.
Okay. So please note it
Okay,
down.
3 to 4, 6 to 7. Okay.
For tomorrow, just for tomorrow. Otherwise, from next week onwards, 9 to 11, 9 to 10, 3 to 4.
Okay, sir.
Okay, you understand, no?
Okay. Yeah.
Just for tomorrow, I have an additional 6 to 7 class. But this is optional tomorrow. And then next week onwards, you have to take from Monday 9 to 11. I will take, of course, Thursday 9 to 10. And then Friday 3 to 4, you will take charge.
Yeah, sure. Yeah.
Okay. All right. Thank you. So we'll close it
Okay.
now. And I'll say.
Thank you, sir.
Thank you very much. Okay.